For this lesson, we are going to look at the chain rule. The chain rule is probably the most challenging bit of differentiation that we are going to be doing in this particular unit. As we get to applications, we will get definitely into some more challenge, but this can be quite tricky. So please, if you don't understand an example, watch it again. We'll be looking at it in a couple different ways. Ultimately, what this is going to relate the most to is composition of functions and looking and seeing if you have a function that is composed of multiple functions put together, then you need to be able to sort of pick apart which function happened first, and then which function happened next, and then which function, just like we were doing in our very first unit. So, if f, big F of x, equals little f composed with g of x, which equals f of g of x, okay? And g prime of x and f prime of x exist. Then big F prime of x equals little f prime of g of x times g prime of x. So we can sort of think of this as the outer derivative of the first function times the inner derivative. Okay, so this is one way to think about it. So you think about you're taking the derivative of sort of the outside function, the function that's happened last, and multiplying it by the derivative of the function that's happened first. When you take the outer derivative, you leave the function it's been composed with inside that function. Another way to think about it that can be easier and actually will relate really well to how we undo this when we get to integration is to use substitution. So to substitute a variable for our inner function. So if we define this as y equals f of u and u equals g of x. So we're going to redefine our g of x as being a variable called u. So what we can say is that dy dx is equal to dy du times du dx. So we're taking the derivative of y with respect to that variable u, not with respect to x, and then we're multiplying it by the derivative of our inner function with respect to x. These two statements both mean the same thing, okay? So these are just two different ways to think about the same thing, the same chain rule, as we call it. Okay, let's look at an example. In this one, you are going to get a bit more time to kind of work through some of the implications of this because this can be quite a challenge. So we are going to find y prime if y equals 3x squared plus x to the power of 5. Now, we could always solve this problem by expanding the brackets, but expanding the brackets to the 5th power, I don't really want to do it. I can't imagine you do. So what we're going to do is we are going to use the second method first. We are going to start by letting u equal our inner function. So the last thing that gets done is that gets raised to the power. The inner function is going to be what's inside. So u is going to be 3x squared plus x. And notice that this is something we can actually take the derivative of. Okay, so if we let u equal that, we get y equals u to the power of 5. Okay, so y prime is going to be equal to dy times du. So we're going to take the derivative of y with respect to the variable u. And I'm just going to write this out in words so you can see it. That is the derivative of y with respect to u. So that means we are treating the u as the variable, and we're just going to take the derivative as if u was the variable. Then we're going to multiply it by du dx, which means we're going to take what u is equal to, which is this 3x squared plus x, and take the derivative of it treating x as the variable. So what does that look like? So y prime, dy du, we have y equals u to the fifth, so dy du is just equal to 5u to the fourth, just as if it were, we're treating u as the variable. Now we're going to multiply it by du dx. Okay, so du dx is going to be the derivative of 3x squared plus x with respect to x. Okay, so here we're treating x as the variable. So we get y prime is 5u to the fourth times the derivative here, which is 6x plus 1. Notice I'm putting it in brackets because we have to multiply by the whole derivative. Now, this is our answer. The only problem is we'd actually like everything in terms of x instead of in terms of u. So we're just going to replace the u with what we started with. So back then we said u was equal to 3x squared plus x. So we have 5 times 3x squared plus x to the power of 4 times 6x plus 1. So we did that using substitution. Without substitution, what you can see is we dropped the power by 1 and multiplied by the number out front, but we left what was inside alone. Then we took what was inside, or our inner function, and multiplied by its derivative. So that's our first way of defining the chain rule. Either way works. We're going to use both. And you can always pick the one at whatever point that you are the most comfortable with. So example number 2, we are going to find f prime of x if f of x equals radical x cubed plus 3. Okay, and let's make this our big f of x. Okay, so let's define a u. So let u equal what's under here, which is x cubed plus 3. So our big f of x is actually equal to u to the 1/2. We could write it as a square root, but it's easier to use the power rule if we use it as a fractional power. Okay, so f of x dx is going to be equal to df du, so we're going to take the derivative of the function with respect to u, times du dx. So if we look right back up there, we've got f of x equals u to the 1/2. So this is equal to 1/2 u to the negative 1/2. So we're just taking the derivative of the function as if the u were the only variable. Now, we're going to multiply it times du dx. So the derivative of our u is going to be 3x squared. And we actually don't have anything else because the derivative of 3 is 0. So we're taking the derivative, we have our derivative of f of x with respect to u, and then we have our derivative of our u with respect to x. So we take the derivative of that u to get that. Now again, we're going to want to replace our u with what we started with. And let's sort of sort everything out. So in the numerator, we're going to have a 3x squared. In the denominator, we're going to have a 2 u to the 1/2 because the negative puts it in the denominator. So in the numerator, we have our 3x squared. In the denominator, we have the 2 from the 1/2. Our u, which is x cubed plus 3, and that's going to be to the power of 1/2, so I can just put a square root. Okay, so notice that this is the same as we're replacing our u back with x cubed plus 3, and we're rewriting to the negative 1/2 as a radical in the denominator. Okay, let's look at another one. How about some trig? Okay, so find f prime of x, so big F prime, if f of x, little f of x, equals cosine x, and g of x equals sine x, and big f of x equals f composed with g. So we're going to apply g first and then f of that. So big f of x is equal to f of g of x. Our g of x is sine x, so this is f of sine x, and our f is cos x, so this is cosine of sine x. Interesting. Now we're going to have to use our chain rule. So let's define our u. So let u, this is our, remember our u is always our inner function, so let u equal sine x. Okay, so big F of u equals cosine u. So f prime of u equals du, df du times du dx. Derivative of f with respect to u is negative sine u times the derivative of sine x with respect to x, which is just cosine x. So this is equal to negative sine of sine x times cosine x. And unfortunately, there's not really anything that we can do to simplify that because we're taking a sine of a sine. It's a composition of functions, not the product of functions. Okay, so let's do one and let's use the other method. So example number 4. Let's do another trig one because trig is fun. So find big F prime of x if big F of x equals sine squared of 5x squared. So this one is a bit trickier and it's a bit harder because we actually have two functions that are inside functions. We've sort of got a triple inside function. So what we want to think is about we have 3 innermost functions and we want to think about what happened. We have to take the derivative of each one. So the very last thing, and we're going to try to think from last to first. Like what was the first thing? So what was the last thing, the most recent thing that happened? And that was the squared. So the thing that we're going to take the derivative of first is we have our squared. Okay, and we're thinking about this sort of in backwards order. Now this is going to remind you when we're taking functions and trying to break them down into what are we composing. So here, the thing we're going to be taking the derivative of first is blank squared. So blank squared, when we take the derivative, we drop the 2 and drop the power by 1, leaving what's inside the brackets the same. Okay, so we're going to start our f prime of x over here. So the very first thing we're going to do is we're going to have 2 sine of 5x squared. Okay, so all we did was deal with the squared. What is the next function? What's our next sort of nested function? So after we squared it, the last thing we did was squared it. Before we squared it, we had to take the sine of something. So the second thing that we're going to deal with is the sine. Okay, so the derivative of sine is cosine. So we're multiplying by the inner derivative. We've already dealt with the squared, so we can ignore the squared now. Now we're just looking at taking the derivative of sine 5x squared. We can't take the derivative. We're not going to deal with the 5x squared yet because that's coming next. So the derivative of the sine is cosine. Okay, so we had our squared, which went to 2 times our blank. Our sine of stuff goes to cosine of that same stuff. So this is times our cosine, and we keep the stuff inside the same. Notice there's nothing about the squared. We dealt with that in the first step. Now third, the last thing we had is we did a 5x squared. And 5x squared goes to 10x. So now we're just going to multiply by that last 10x. And there's nothing inside that we would need to take the derivative of. Once we get to something where we can just take the derivative with respect to x, we're done. So last thing that happened to it was squaring, next to last thing was sine, and the very first thing that happened to the x was 5x squared. So now we have all of this stuff. We had to take an outer derivative, kind of a middle derivative, and then the very innermost derivative, and multiply them all. Let's simplify this mess. So we have 2 sine x cosine x. So this is equal to 20 sine 5x squared cos 5x squared. One thing I might notice, though, is that 2 sine x cos x happens to be, just to simplify, 2 sine x cos x is equal to sine 2x. And since I already have quite a mess inside, I may as well just rewrite this, take a 2 in as 10 sine 10x squared. And that looks quite a bit simpler, doesn't it? Lovely. Okay, so that's just a reminder. And our 10x, as we can see, if we have a 5x squared, doubling that gives us a 10x squared. Okay, last one, another, well, maybe not last one. Let's do 2 or 3 more. This is tricky. I would like to give you a few examples to kind of latch on to. Okay, so we've got example 5. Let's find the derivative, okay, of 5x plus 2 over x cubed dx. Okay, so rather than deal with our assigning a variable again, you've had a few ones where we assign a u. We could assign a u, but we're not going to bother. We have 2 things that are happening. The first thing we're going to deal with, our outer function, so let's call this the outer, the most outermost function, is going to be stuff cubed. And then our inner function is 5x plus 2 over x. Now we don't need to use the chain rule at all on the inner function because it's not a composition of functions. It is a quotient of functions, so we will in the end need to use the quotient rule, or we're going to need to rewrite everything as powers. So if you wanted to rewrite it as powers, you could rewrite this as 5 plus 2x to the minus 1, which I actually find quite a bit easier. Okay, so our outer derivative says that we are going to be, our cubed goes to being 3 times stuff squared. So we are going to do 3 times the same stuff, 5x plus 2 over x squared. So that's our outer derivative. Our inner derivative is taking the derivative. Now we have to multiply by the inner derivative. So the inner derivative is 5, derivative of that is 0, plus 2x to the minus 1, multiply by negative 2, and we get negative 2x to the minus 2. Okay, and we could leave it like that. I don't really like that squared, but I think that we are potentially going to have to live with it. Okay, if you like, you can rewrite it as negative 2 over x just to make things a bit simpler, and then multiply by another x squared. Okay, example 6. We have another multi-trig one, so let's have y equals cosine cubed of radical x. That one's lovely. How many functions do we see? I see 1, I see 2, I see 3 functions that are kind of nested inside each other. So we have our outer function. The outermost function here is cubing, which goes to 3 times stuff squared. our middle function, we have a middle function. And that is our trig function. Remember, the cubing is cosine with the little cubed here means we're cubing the whole thing. So that is why that is our outer function. Our middle function is cosine of stuff, which gives us, when we take the derivative, negative sine of stuff. And our inner function is x to the 1/2, which gives us 1/2 x to the minus 1/2 using our power rule. So now we're going to have to just multiply those all together to get our y prime. So y prime is 3 times stuff squared. So 3 times cosine squared radical x. And you don't really even need these outer brackets. We can just write it like that because we can do the squared right there. So 3 cosine squared x times minus sine of stuff times minus sine of radical x times our inner derivative, which is 1/2 x to the minus 1/2. So this is all going to be divided by 2 radical x, which is the same as 1/2 multiplying by 1/2 x to the minus 1/2. And there are many different ways we can write it. We know that there's going to be a negative. We may as well bring that negative out front. There's not a whole lot of other simplifying you can do. You can be dividing by radical x. You can put the radical x out front. Many different ways to write this correct answer. Okay. Example 7, very last one. Okay, we want to find the equation. Remember, we can still use this to find the equation of the tangent line. That was our whole motivation for derivatives in the beginning. So we're going to find the equation of the tangent to y equals x squared minus 7 to the power of 4. At the point 3, 16. Okay. So our slope equals y prime evaluated at x equals 3. So let's do got our y is x squared minus 7 to the power of 4. So our outer function is stuff to the 4th, and our inner function is x squared minus 7. So our stuff to the 4th is going to give us 4 stuff to the cubes, 4 stuff cubed. So y prime is going to be 4 times x squared minus 7 cubed times the derivative here, that's just 2x. So times 2x. So now I'm going to evaluate y prime at x equals 3 is 4 times 3 squared minus 7 cubed times 2 times 3. Okay. So 3 squared is 9 minus 7 cubed is 8. 8 times 4 is 32, and 32 times 6 is 192. So our y, we're going to come up with the equation of a tangent line. We're not done yet. We've got our slope. So it's quite a steep slope, as you can see. Y equals 100 would probably be pretty indistinguishable from a vertical line if you were just looking at it. So we've got y equals 192x plus b. We have a 3 and a 16, so 16 is 192x plus b. And we're going to plug in 3 for x. And solving for b, we get b equal a negative 560. Okay, so y equals, so our equation of our line is y equals 192x minus 560. And that is our final answer. Okay, so as you work through your chain rule problems, please do remember this is probably the trickiest thing we do in this entire chapter. And the chain rule is something that just kind of keeps on going. You find what happened, what's your outer function, what comes next, what comes next, what comes next. You're breaking down and taking functions that are compositions of functions and trying to decompose them into pieces that you can take the derivatives of.